So on slide 24, we now move from the single indicator situations that we've looked at, and we'll take a closer look at multiple indicators per time point, which is really the setting that latent transition analysis is focusing on. We're going to take a look at this from a psychometric perspective, where we'll get into issues of measurement non-invariance and multi-level modeling of both factor analysis and latent class analysis. Slide 25, we have a situation where we are concerned about response bias in self-report questionnaires. So it has been mentioned in the psychometric literature, starting with 1940s psychometric monograph by Wolf, concerns about the individual differences in intercepts and loadings in factor analysis models due to response styles like acquiescence or social desirability. And this was picked up by Maydew, Olivares, and Kaufman in 2006 Psychological Methods, where they introduced the random intercept factor analysis, where individual differences are captured by an added response style factor with factor loadings fixed at 1. So it is a random intercept factor. Different individuals are allowed to have different intercept values. This has been applied, for instance, in European Journal of Psychological Assessment this year by Schmalbach, from bidimensionality to unidimensionality in self-report questionnaires, with applications to a series of established questionnaires for depression, procrastination, etc. So the model that Maydew, Olivares, and Kaufman considered looks like this. Once again, if you just look at the picture, it looks quite familiar, with a random variable sitting up here, be it a random intercept or a latent trait, influencing different variables the same way with loadings coefficients 1. Down here you have the factor analysis model that you're interested in, with its loadings lambda 1 through lambda 5. And in formulas for a categorical outcome U, you look at the logit of that as a function of the factor. We have an intercept, which is varying across the variables, the factor indicators. R goes from 1 through 5 in this case. Nu is how you read that symbol, using the literal all Y type of parameterization notation. And then you have a random intercept part here, U sub I, varying across individuals I. And then you have the factor model that you're really interested in, lambda for item or indicator R, multiplying the factor value for individual I. So here we then have a random intercept with mean 0 and variance sigma squared. Alternatively, you could say that the mean is nu R and put the mean in here. But it's the same thing. UI is a random intercept factor with loadings fixed at 1 for all the factor indicators. So we actually add only a single parameter, sigma square, the variance of this, to the regular factor analysis model. And by being able to pull that U random intercept variation out of the U variables, F, the influence of F, pertains to what's left in the U variables. So taking into account or taken care of the variation across individuals that's constant over all items, and eliminating that before you do the factor analysis. So essentially then we're capturing measurement non-invariance by this random intercept. That is, the measurement qualities, in this case the intercept, vary across individuals. So it should allow for better estimation of the model of interest, namely the factor loadings. And it suggests also that measurement non-invariance is okay if modeled. But you can ask, is the model really realistic? Different indicators may have different random intercept variance after all, but we can't identify that. What we would need to be able to identify that is a design where each indicator is measured multiple times, such as with multi-level data, students nested in schools, so you can have a factor analysis intercept that can vary across schools. Or longitudinal data where time is nested within individuals so that an intercept for each indicator is allowed to vary across individuals. So the random intercept factor analysis model is useful because it takes a step in the direction of capturing measurement non-invariance in the sense of an intercept parameter being different for different individuals. But there are other settings where we can go a little bit further in terms of allowing for measurement non-invariance.